Hello, I am Philippe Devloo and I'm going to present the master's thesis research of Gustavo Batistella and Victor Oliari. They both finished their master's research work and are working for external companies at this point, so I'm going to present their work. As a general context of this research, the global aim of the participation of LabMech in the EPIC project is to develop a fast prototype reservoir simulator based on multiscale approximations. So at the first part, we developed a reservoir approximation based on average cell pressures, which gained us a lot of CPU time. We implemented the reservoir simulator with the image and multiscale method so as to reduce the size of the global system of equations. We developed a specific HDiv approximation space with constant divergence, which greatly reduced also the global system of equations. We are working on a fast iterative solver for HDiv saddle point matrices with Jefferson, which is going to reduce the size of the system, has to be solved with a direct solver. And this is the context of this work. So Gustavo worked on an error estimation of MHM approximations and incorporated adaptivity. The reason for that is if you reduce the size of the equations through the multiscale method, there are certainly problems for which the MHM method induces a large error. And so performing error estimation and adaptivity, we solve this problem. And Victor has worked on the optimization of the stiffness assembly and has compared the execution type using different flavors of the multi-thread library. So the presentation has two parts. First I'm going to present the work of Gustavo Batistella, which worked on the error estimation and adaptivity. In the second part I'm going to present the work of Victor Oliari, who has compared HDiv approximation with hybridized H1, compared CPU performance of both approaches, and proposed an error estimator. So adaptivity applied to the multiscale hybrid mixed method. The equation reduction, as I already said, that MHM results, it comes at the price. It's easy to identify problems where MHM yields poor results. But if we use a posteriori error estimator together with adaptivity, we can turn MHM into a more reliable tool. So Gustavo's research has been published in the International Journal of Numerical Methods in Engineering. The work was developed together with Denise Siqueira from the Technical University of Paraná and Sonia Gomes from the Department of Mathematics. So what is MHM? The basic idea of MHM is to divide the domain into coarse scale polygons. Each polygon is discretized with fine scale elements, and the fluxes between the polygons are what we call coarse scale fluxes. So in this slide you can see the subdomains omega 1 and omega 2, and between omega 1 and omega 2 we consider the flux to be linear. So that means that the global system of equations corresponding to the connections between microdomains is reduced to those global fluxes. So we have a small global system of equation, and within each microdomain we need to condense the local equations onto those coarse scale fluxes. In terms of an error estimator, we use the Prague-Sinja theorem, which says that if we have an HDiv approximation of a given solution, and we project this HDiff approximation onto an H1 function, the difference between the HDiff approximation and the H1 function is representative as an upper bound is larger than the approximation error of the HDiff approximation. So the whole idea is to project MHM approximation onto an H1 function. So how do we do that? So we, on the top left, you can see the MHM approximation of an oscillatory problem. You see it is discontinuous. So first we combine, we take the average at the nodes, at the nodal intersection of the MHM domains. Once we have those nodal values at an average, we use this as an input to compute the nodal averages of the sides. Those averages depend on the relative permeability on each side. And then once we've done this averaging, we have a projected solution. So the idea is to take this discontinuous solution, project it using local operations onto an H1 solution, and the difference between those two approximations is going to be our error estimation. One way of computing the quality of the error estimation is to compute an effectivity index. So the effectivity index is the ratio between the estimated error and the exact error for each subdomain in this case. So here we take a very smooth solution. We simulate this problem on this 4x4 microdomains, where each microdomain has a 2x2 mesh. We compute the exact error, we compute the estimated error, and we see the effectivity index is between 1.062 and 1.057. So the effectivity is very close to 1. I have to say from experience that computing effectivity indexes of smooth solutions is not easy, it's very hard. Okay. We did the same thing for the error estimation of a singular problem, and then we incorporated refinements. So we tried two kinds of refinements. I come to that later. So here we have the exact solution represented, so it has a very strong peak, and then within this microdomain we computed the error, and based on where the error was larger, we refined the skeleton mesh each times more. And so when we compare the refinement of the skeleton mesh, we have this curve, so this adaptive process we have developed. If we would divide, if we use uniform refinement, we get this curve. If we refine the microdomains in the region where the error is larger, we get to this curve. So we developed a very efficient error estimate adaptive procedure for MHM approximations. We also applied this to the one of the cross-section of the SP10. So we divided this domain into microdomains. You see here the permeability in the log scale, so very permeable here. There's like a permeable channel here. If we don't refine the MHM domains, this linear flux is going to block the passage of the fluid. So here we have the adaptive mesh. You can see wherever the those dots between the microdomains are small, it means that the skeleton mesh has been refined in order to diminish the approximation error, the energy approximation error. And if we combine uniform refinement with adaptive refinement, it's okay, it's not fantastic. And I believe, we still have some work to do on this. So as a conclusion, we have developed an efficient error estimator for MHM multiscale approximations. Effectivity index for smooth solution is very close to 1, so very efficient error estimator. We developed an adaptive strategy based on the division of the skeleton discretization between microelements. We obtained a very good error in terms of number of degrees of freedom, and we published this research in a very good journal, the International Journal of Numerical Methods of Engineering. The second part of this presentation documents the work of Victor Oliari. So at the beginning, I mean, maybe still, but we noticed that HDiv approximations are inherently expensive. So we approximate both the flux variable and the pressure variable into one global system of equations, which is much more expensive finite value methods. We observed that the hybridized H1 approximations yield similar approximation errors as HDiv, and the hybrid H1 approximation are also element-wise conservative. So the work of Victor was to compare HDiv with hybridized H1. So eventually we would switch our solver from our reservoir simulator to hybridized H1 if it would be more efficient. And considering the similarity of HDiv and hybridized H1, we developed a posteriori error estimator for hybridized H1. So what's hybrid H1? In hybrid H1 we have a discontinuous approximation space for the pressure, and between the elements we have a Lagrange multiplier which represents the flux between the elements. The second equation, the equation associated with the Lagrange multiplier, is to weakly enforce that the jump of in the solution between the elements is 0, or in the Dirichlet condition is weakly equal to the Dirichlet value. Okay, so the global system of equation consists of internal pressure equations and between the elements flux equations. Okay. Most of the pressure equations can be condensed onto the boundary fluxes except for the constant pressure. And the global system after condensation is exactly the same as the HDiv matrix. In HDiv approximations, we have an approximation space for fluxes, an approximation space, discontinuous approximation space for pressures. The main equation is the corresponds between the permeability, the inverse permeability applied to the solution multiplied by the flux is equal to the pressure. And the second equation, the equation associated with the pressure variables, is imposing that the divergence of the flux is equal to the source term, which is often 0. Okay, so we have an approximation space for fluxes and pressures. Internal fluxes and pressure equations can be condensed on the boundary flux degrees of freedom. So the structure of the global system of hybrids H1 and HDiv are absolutely identical. So if we compare approximation errors, in the mixed method it is possible to use lower order pressures. So we have this convergence curves for the pressure, but if we increase the number of bubble functions in HDiv, then we see that the HDiv approximation and the hybrid H1 approximation yield very similar results. For the fluxes, both approaches yield very good, very equivalent results. So there basically are two methods which give more or less the same result. We did the same comparison in 3D. So Victor in all his work has done the work both for 2D approximation and 3D approximations. if we compare in terms of execution time, and this slide actually hides a lot of work. So Victor, together with a collaboration of the National University of San Agustin of Arequipa, Peru, they worked on optimizing both the hybridized H1 approximations and the HDiv approximation. So they used BLAS and LAPAC in all operations, did profiling, and reached to a point where optimization was difficult without restructuring code. And we note that the approximation error of the flux space for hybrid H1 and HDiv, comparing the time in terms of the approximation error, they're totally equivalent. So the HDiv approximation have more degrees of freedom, but they need to be condensed. The hybridized H1 had to, in order to have a stable approximation of linear fluxes, had to go to cubic approximation in the interior, and so that is expensive. And so that's what makes that for both 2D and 3D approximations, the hybridized H1 and HDiv are totally equivalent. Victor also worked on parallel acceleration of the assembly process. So we compared many parallelization techniques. So one was a producer-consumer process. We implemented a parallelization technique based on mesh coloring. We implemented parallelization using atomic variables. And we also implemented parallelization using thread building blocks. We tested this acceleration process on a Dell computer with Xeon processors. There's 16 processors and a lot of central memory. What we observed is that for when you used mutexes, and so you see here the curve, which was absolutely not efficient in terms of parallelization, we saw that the use of mutexes had incurred a large efficiency loss. Okay, so we also observed that we were able to accelerate only a factor of 8 with 16 processors. So we can't really explain it. It's very hard to evaluate which part does not accelerate properly. But all the techniques we implemented had the same behavior. So we think that probably the less than ideal acceleration is due to memory access. Okay, so we used the fact that hybrid H1 is similar to HDiv to use the techniques that Gustavo developed for projecting the discontinuous H1 approximation onto a continuous space. And as we have the boundary fluxes, we were also able to project the discontinuous solution onto an HDiv approximation. So we verified the error estimator for this singular problem, and we see that our effectivity index for the different orders of approximation was not as good as the effectivity index for our MHM-HDiv method. Instead of being close to 1, it's about 1.6. It overestimates the error, which means we are on the safe side. Okay, so as a concluding remark, so the work of Victor, we did a detailed study comparing hybrid H1 and HDiv. We've shown that the errors are similar for comparable element sizes. The errors are the same when computed as a function of CPU time, so they're really equivalent methods. We studied many parallel acceleration techniques with the available parallelization tools we had. So we observed most tools yielded exactly the same acceleration, and we also concluded that mutexes should be avoided in the computing in parallel computing of in cheaper matrices that are less CPU intensive. Finally, we developed an error estimator which resulted in an effectivity index of around 1.6. The work on the error estimate has been submitted to a journal and is under review. So we thank Unicamp, Equinar for the scholarships, FAPESP, ENP, Unicamp for providing some of the problems, Cepatro for administrating the project, and FAC is the School of Civil Engineering where we are working. Thank you very much.